Hi guys, and welcome to video number 27 in the But How Do It Know companion video series. Today we are going to look more closely at 4 new instruction types or families that are going to provide invaluable capabilities to our CPU. In fact, most of what we're going to look at today is what will allow our CPU to become a truly general-purpose computer. The instructions that we have seen so far are great, and they allow us to make use of our ALU, registers, and RAM to actually do stuff. But we don't have much flexibility in the way we can order these instructions. We can basically only execute them sequentially. As mentioned by John on page 128, we will very quickly run through our maximum 256 instructions and hit the end of our RAM. Furthermore, much of the algorithms used in computer programming involve repeating things over and over, but there is no way for us to do that besides copy-pasting the instructions repeatedly. This brings us to what John calls the second great invention, namely the concept of jumping. Jumping means having the ability to set a specific value in the IAR instead of always having it increment by 1 all the time. The first jump instruction that we have is the JMPR instruction. It allows to jump to an address contained in the specified register. The JMPR instruction always begins by 0011. The next 2 bits are always 00, and the last 2 indicate from which register we want to take the address. As you can see, the JMPR instruction circuitry is really simple. It only uses one stepper step. During that step, it simply enables regB and sets it to the IAR. The second jump instruction is more direct, allowing us to specify the address in the data byte just like the data instruction. The jump instruction doesn't have any parameters. It is always 0100 0000. In the next byte, you specify the address to which you want to jump to. The jump instruction schematic is also quite simple. During step 4, it enables the IAR, which has already been incremented to point to the address byte, and sets it to MAR. Then, in step 5, it takes the contents of RAM at MAR, which is in fact our address byte, and sets it to the IAR, thereby redirecting the rest of the program. As useful as both these instructions are, we are still missing something. Let's say we want to execute a series of instructions, say 100 times. At the end of our instruction block, we can increment a register to keep track of how many times we have performed our loop, and then place a jump instruction to go back to the top and repeat. But when our counter has reached 100, we have to skip that jump instruction because we have finished our 100 iterations. So in many cases, we need the ability to jump sometimes. That feature, called branching or conditional jumping, is what John refers to as the third great invention. But what can we use in our CPU as values to decide if we should perform a jump or not? If you remember, when we looked at the ALU in video number 14, we had 4 signals, or flags, that the ALU can set while it is performing its operation. Those were carry in, A larger, equals, and 0. We can use the values of these 4 flags to decide if we will jump or not. For example, we can use the CMP operation to compare 2 numbers and then jump if A is larger. There is a flag for that. So there's actually a family of conditional jump instructions. The first 4 bits are always 0101. In the next 4 bit, you specify for which of the different ALU flags you want the jump to happen. So, for example, if you wanted to jump if either the carry flags or a larger or 0 flag was on, you would set 1101. Then in the next byte, just like in the last instruction, you specify the address that you want to jump to. In order to implement conditional jump instructions, we need 2 things that are not currently on our project board. the flags register, and the conditional jump circuitry. The flags register is used to remember the ALU flags after an ALU operation so that they can be checked later. It is a regular register of which we will only use 4 bits, one for each flag. The conditional jump circuitry can be seen on page 134. It checks if one of the requested flags in our conditional jump instruction is on. If that is the case, it outputs 1, or else it outputs 0. Steps 4 and 5 in these instructions are exactly the same as steps 4 and 6 in the data instruction. We set MAR to IAR in order to prepare to get our address byte, and we also increment the IAR in case we don't jump and need to continue normally. In step 6, we enable RAM to send our address to the bus. Then one of two things will happen. 1, the conditional jump circuitry outputs 1, and we perform the jump. This means that at least one of the flags specified in the instruction is on. In that case, the AND gate for step 6 is on and our address is set in the IAR. 2, the conditional jump circuitry outputs 0 and we don't jump. The AND gate for step 6 is off and we do nothing. This special instruction is actually what makes our CPU Turing complete and allows it to perform any task that is computable. Finally, there is the clear flags instruction that sets the flags register to all zeros. The clear flags instruction is always the same. 0, 1, 1, 0, 0, 0, 0, 0. It doesn't have any parameters. It clears the flag very cleverly in one step by simply enabling bus 1, thereby causing the ALU to perform a 0 plus 1 addition, which it turns out leaves all of the ALU flags off. It then sets the flags register with this result. That's it for this set of instructions. In the next video, we will be adding the flags register and the conditional jump circuitry to the project board. See you soon!